Now we're going to look at fundamental problem 7. In fundamental problem 7, we read that a particle moves along a straight line such that its acceleration is 4t squared minus 2, which is in meters per second when t is in seconds. When t is equal to 0, the particle is located 2 meters to the left of the origin. When t is equal to 2 seconds, it is 20 meters to the left of the origin. Determine the position of the particle when t is equal to 4 seconds. So we want the position S when t is equal to 4 seconds. They did not tell us in this problem what the positive direction is, and we need to know that because they give us the equation here, which is going to determine the sign of A. So let's assume that to the right is positive. So in this book, they indicate the positive direction like that. So if to the right is positive, if we're to the left of the origin, that would be negative. So when t is equal to 0, the particle is 2 meters to the left of the origin. So this is going to be negative 2 meters. And we're 20 meters to the left of the origin when t is equal to 2 seconds. So that's minus 20 meters. Okay, so they really should have told us in this problem that to the right was positive. Okay, now we're all set to find the position at 4 seconds. Okay, we have acceleration as a function of time. Looking at our equation sheet here, we have this equation which relates acceleration, velocity, and time, and we have this equation which relates position, velocity, and time. But I don't think we need to think too hard about this because hopefully we remember from Physics 161, if you integrate acceleration with respect to time, you get velocity. If you integrate that with respect to time, you get position. So we just have to integrate the acceleration twice with respect to time, and we will get a function of position with respect to time. So first we want to find position as a function of time. So for this we are going to use equation 12-2, rearranging it by bringing the dt over to the other side. We have dv is equal to a dt. I take the acceleration that they gave me, I put it in here, and I get dv is equal to 4t squared minus 2 dt. And then I'm going to integrate. Okay, now we have acceleration. We're looking for position. So when I integrate the velocity here, well, I'm looking for position as a function of time, but first I want to get velocity as a function of time. Okay, so I don't want to actually put in a value for my upper limit of integration because I want the velocity as a function of time. So the upper limit of integration, I'm just going to call it v, and this isn't a specific value of the velocity. It's going to give me the velocity at any time t, which I could plug in any value of t that I want to get the velocity at that time. For the lower limit of integration, I want to use 0 for the time, and if time is equal to 0, then the position would be s0, the velocity is v0, the acceleration is a0. That just means the position when time is equal to 0, the velocity when time is equal to 0, and the acceleration when time is equal to 0. Similarly, if t was equal to t1, the corresponding position, velocity, and acceleration would be s1, v1, and a1. And when t is equal to t2, we have s2, v2, and a2. So you're not necessarily saying what the position, velocity, and acceleration are. You're just saying this is the position at time 1, or the velocity at time 1, or the acceleration at time 1. Okay, so when time is equal to 0, my lower limit of integration on the left-hand side is the velocity when time is equal to 0, so that's v0. Now, I'm going to have to figure out what v0 is before I finish the problem, but for now, I can just call it v0. Okay, so then I integrate. On the left-hand side, I'm just integrating dv. So I just get v, and I plug in the limits of integration, and I get v minus v naught. And then, on the right-hand side, I integrate, and I get, this would become 4t cubed divided by 3, and this would be t2, and then I evaluate from 0 to t. Well, I started writing it. I guess I'll finish writing it. But you just get the same thing, because when you plug in the upper limit of integration, you just get what we had to begin with, right? And when you plug in the lower limit of integration, you get 0 for this term and 0 for that term, so that doesn't change anything. But I want the velocity as a function of time, so I'm going to take this v naught and bring it over to the other side, and then this is the velocity at time t. So that would be plus v naught. So now we have an equation for the velocity. And then, going back to my equation sheet, we have v is equal to ds over dt. I can bring the dt over to the other side. Let's write it this way though. ds is equal to v dt. And then I can take the velocity equation that I have here, plug it in here, and then integrate. So I have this. Again, I'm going to have to choose limits of integration here. Whoops, this is supposed to be a dt, just like it was there. The lower limit of integration, I'm going to say, is when time is equal to 0, and the upper limit of integration is just when time is equal to t. We could say this also, when t is just equal to t, the position is s, the velocity is v, the acceleration is a. And that would be an arbitrary time, an arbitrary position, an arbitrary velocity, and an arbitrary acceleration. So when t is equal to 0, the position is equal to s naught. I actually know what that is, right? Because they gave that to me up here. But I think I would just like to keep it as s naught for now. And just like the v naught that I have here, I'm going to have to figure out later what it is, but actually I don't have to figure it out because I already know. It's -2 meters. Okay, and then when time is equal to t, the position is equal to s. When I integrate on the left-hand side, this is similar to what I did for the velocity. You just integrate ds, you get s, you plug in the limits of integration, and you get s minus s naught. And then here, when we integrate t cubed, we get t to the 4th divided by 4. That 4 in the denominator is going to cancel out the 4 that I have here, so that's 1/3 t to the 4th minus 2t. When I integrate that, I get just t squared plus v naught, which is a constant. So when I integrate that, I get v naught times t. And then I have to evaluate it using the limits of integration, but when I plug in the upper limit of integration, that just gives me what I have here. When I plug in the lower limit of integration, this term is 0, this term is 0, and this term is 0, so that doesn't change anything. Okay, so then finally, I just want to take the s naught and bring it over to the other side. So I have s is equal to 1/3 times t to the 4th minus t squared plus v naught times t plus s naught. And this is what I set out to find. This is the position as a function of time. Now that I have this, I can find the position when t is equal to 4 seconds. However, if I just take 4 seconds and plug it in for the time, I still have the v naught and the s naught here. So right now I have 2 unknowns. But the s naught actually, like, it's not really an unknown because I know it's -2 meters. So I could go ahead and plug that in for s naught. But then I still have one unknown. But fortunately, they gave me a second piece of information here. When time is equal to 2 seconds, the position is equal to negative 20 meters. So I can use that to figure out my last unknown. Okay, so let's rewrite the equation with a negative 2 for S naught. So that's minus 2. And then I can find V naught by saying when time is equal to 2 seconds, I have 1/3 times time is equal to 2 seconds, so that's 2 to the 4th minus 2 squared plus V naught times 2 minus 2. This has to be equal to negative 20 meters. Okay, I want you to solve that on your own. Okay, so you can go ahead and plug that into your calculator after you bring everything except for the V naught times 2 over to the other side. Then divide by 2, and you should get negative 29 divided by 3, which is approximately equal to negative 9.67. So then, you get to solve that on your own. Then I have the position as a function of time. So going back to the equation that we had here, but putting in a negative 29 divided by 3 for V naught, I have 1/3 times t to the 4th minus t squared minus, this was exactly 29 divided by 3. You can use that negative 9.67 if you want to. That doesn't matter to me what you do for that. Okay, so now we have the position as a function of time, and we can just go ahead and put the 4 seconds in and see what we get. So finally, the position when time is equal to 4 seconds is 1/3 times 4 to the 4th minus 4 squared minus 29 divided by 3 times 4 minus 2. And you can go ahead and plug that into your calculator, and you should get approximately 28.7. And this is position, so the units would be meters. And that concludes fundamental problem 7.